So let's get started. Okay, so I know that it's the holiday week, all right, and maybe quite a few of our batchmates may be busy with other matters, all right, so they may just choose to watch the recording. Okay, so in the interest of time and those who are already here, let's get started. Okay, um, yeah, so I think all of you read the news about the NUS professor who went on a 2-hour lecture without realizing that he was on mute. Okay, uh, so I hope that doesn't happen to anybody else. So if anything goes wrong and you really can't see me or hear me, I think I've shared my number with you all. Okay, in case you all don't know. So anytime you need to contact me, you can always directly contact me. Okay, students will usually message me if they want to uh, clarify anything. Okay, so today's plan. Okay, thank you. Okay, for the message. I can hear me well. Okay, so for today's plan, basically, I'm going to start off with the tutorial. All right, to go through the tutorial 2 questions. After that, I will briefly run through the Qt Spin software so you understand how to use it, and and that will give you the confidence to approach the assignment questions. Okay, and once we are done with that, we can start with the next chapter, which is on the instruction set format. Okay, so let me get started. All right, so let's start off with the first question. So in this first question, we are looking at bit masking, or in a sense, yeah, bit masking to logical operations to that we can perform on variables or any form of data. Okay, and these operations are actually very critical and important for us, uh, especially when we are looking at the assembly language programming, where we want to focus on specific bits in a register. All right, so we will look at more examples later on. Okay, so in this question that is given to us, okay, what you have is we have used type define. Okay, so if you're not familiar with type define is a way to give a new name for a data type. All right, so this unsigned character is of course what is already supported within the C framework. Okay, but if you want to give yourself a new data type name, okay, why would you want to do that? Because sometimes the data type name can reflect better the type of information it holds. Okay, so in some cases you may want to just use a different name, okay, for the data type that you are going to use. So in this case, what we have done is we have used type define to say the unsigned character can also be represented using another shorter form called byte t. All right, so in the code here, when I say byte t, okay, what is happening is I'm actually uh, this actually will be replaced with unsigned character. Okay, when you are going to compile the code. Okay, basically the byte t is just a short form representation of this unsigned character. Okay, so now you have two variables A5, B22. Okay, and the first two instruction is to print byte. Okay, so I will not go through the print byte function. Okay, the print byte function is basically to print out character by character. Okay, I will focus more on the actual or the logical operations here. So A and B. Okay, so A is 5. Okay, A is 5 and B is 22. Now, a character is, of course, 8 bits, and we are going to use 8 bits to represent this information here. So 5 should be quite easy. It is basically 0, 1, 0, 1. So the upper bits will be 0. Okay, for 22, if you're not very sure, I mean, if you look back at the notes, we know that to convert between integer and between a decimal number and binary, you go through the divide by two process. Okay, but if you want to make your life easy, okay, you can just use your calculator. Okay, so in your Windows system, okay, you will have this built-in calculator where you can change the mode of operation. All right, usually by default it is in the standard mode. Okay, you can change to programmer. Okay, most handheld calculators also support this kind of basic conversion operations. So in this case, I have decimal 22, and that is represented in binary. Okay, so I can put it down here. So it's 0001 0110. So it's 0001 0110. Okay, uh, and in the first example here, we are doing an OR operation. Okay, so I'll just show you one example and then we'll go to the code. So if you remember OR basically says that you want to draw the truth table for OR. You have 0 0 0 1 1 0 and 1 1. So for the OR operation, as long as any input is a 1, the output is a 1. So this will be a 1 1 and 1. This will be a 0. Okay, so over here the result of A or with B, you will get 1 1 1, here 0 1 0 0 0. Okay, so you can of course try all the different types of operations. Okay, so let me go and show you the code. Okay, so this is the online compiler, online GDB compiler, which is very easy and user friendly. Okay, so if you look at this operation here, what we have is this the same code as just now. So maybe I'll just show an example of this just to make sure you understand how this part works. Okay, so this is the code that is doing the printout. Okay, so this is basically what you call a ternary operator, this question mark here. And what it does is it is a sort of a compressed if-else statement. Okay, it's a compressed if-else statement. So this is actually equivalent to saying that if x end with 0x80, I want to put a logical one, sorry, a character one, else it is a 0. Okay, so this is basically what we are doing here, and this can be represented in a short form representation using this ternary operator. So this question mark basically tests whether this condition is true or false. Okay, so if it is true, I take the first option. If it is false, I take the second option. Okay, so that is how the print byte code works. And over here, when we're doing an AND operation, so here we're doing an AND operation with 0x80. So when I look at my x is an 8-bit value, and I'm doing an AND with 0x80. So 0x80, if you were to put it in binary, it is 1000, okay, 0000. So for AND operation, anything AND with a 0 will be a 0. Correct? So if I were to draw a line here, basically all these lower 7 bits will automatically become 0. And I'm just interested in the first bit over here. So if the first bit is a 1, the output will be a 1. Okay, the first bit was a 0, the output here will be a 0. Okay, so that is what that whole sequence of print byte is doing. It is checking bit by bit. So 80, 40, 20, and 10, and so on. Okay, so that is what the print byte function is actually doing for us. Okay, so if I were to run this code over here, okay, so you can see the printout here is the same as what we saw earlier 00101111. Okay, so let me just extend this a bit, okay, to add in another function. Okay, so I do an AND. Okay, so here I'm going to do an AND operation between A and B. So if I were to do an AND operation, okay, coming back here, you will see that if I were to do an AND, okay, what you will see for AND operation, as long as any one of the bits is a 0, the output will be a 0. So the last bit here will be a 0, 0. This will be a 1, then 0, 0, 0, 0, 0. Okay, because there's only one bit position where both of them are 1. Okay, so that is the expected answer. So we can confirm it over here. Okay, so there's a question how to convert 80 to binary. Okay, so let's look at this first. So the result is what we saw just now, 00000100. Okay, so this 0x80 is basically a hexadecimal, correct? So for hexadecimal, every hex digit is represented by a 4-bit binary. Okay, that is the hexadecimal format. So in 4-bit binary, 8 is 1000 and this 0 is 0000. Okay, so that is how you convert hexadecimals to binary. So it's very straightforward. You just take every bit or every digit in your hex and convert it to the equivalent 4-bit binary number. Okay. Okay, so let's try just one more operation here. Okay, the rest of it you can just key in some compiler and you can see for yourself how this works. Okay, so now instead of doing an OR or an AND, okay, what if I put a double AND? Okay, so what's the difference between a single AND and a double AND? Can anybody tell me what's the difference between a single AND, A and B, and A and B? Anybody want to share what you think is the difference between both of this? Yes, correct. Okay, so the difference is one is a bitwise operation, the other is a logical operation. All right, so what do I mean by that? So coming back here, what we did just now, all right, is what we call bitwise. Why? Because I did individually, I look at the bits, correct, and I do the AND operation or the OR operation. But when we have logical Boolean operation, that means A and B, this is equivalent to saying this particular variable doing an AND operation with this. All right, that means I treat the whole A and the whole B as a single Boolean representation. That means it's either true or false. Okay, so I don't look at bitwise operation. I think of the whole thing as a Boolean operation. Now, so when I look at the whole representation as either being true or being false, and the way you interpret this is anything as long as it is 0, that means all of them are 0. The entire, whether it's 8-bit, 16-bit, or 32-bit, only when all of it is 0, then you say that that is a logical 0. If along the bits, any one bit is a 1, doesn't matter the location. Any one bit is a 1, that means it is considered a non-zero number. Correct? So as long as it's a non-zero value, you can represent it as a logical 1. Okay, so it doesn't matter where the 1 is. But as long as there is a single 1 somewhere, that means it is not 0. So if it's not 0, it is considered a logical 1. Okay, so now if you look at A and B, okay, you see that both A and B are considered to be Boolean true, correct? Because both of them have a 1 inside. Okay, both of them have 1 inside. That means over here, if I come back here and I run this code now, okay, you can see that the result here is 1. Okay, uh, 0, 0, 0, but the last bit is a 1. So that tells us that this Boolean operation is actually true. Okay, similarly, okay, let's try if I put another variable C and I say C equals to 0. And instead of A and B, I put A and C. Okay, so in this case, C has a value of 0. That means it is all the bits will be 0. So if I do a run now, you will see that the answer here is 0. That means it's a false because C is considered a false, A is considered true, true and with false will give you a false. Okay, so that is how you can sort of review your bitwise operation and logical operations, okay, using this code that is given here. Okay, so any questions? If no questions, okay, if you have questions, you can just type in the chat or you can unmute and ask. Okay, if not, I will just carry on to the.
Can I ask a question?
Yeah.
What if we use negative numbers for this question?
Okay, so in this case, even if you use negative numbers, it will still be represented in the same 8-bit value, correct? And it does not make a difference because we are doing bitwise operation. Okay, so even if so for example, okay, if I create a variable called D, okay, if I create a variable D and I say it is -5. All right, so in terms of representation, okay, if you use a calculator, for example, if you say 5 negative, okay, if you look at the last 8 bits, is 1111 1011. Okay, so as far as the code is concerned, because we are not looking at the value in any way, we are just doing all bitwise or logical operation, it will not really matter. Okay, so for example here, if I say D is -5, okay, so let me do a printout of D. Okay, so you will see that D is represented by what we saw just now, 1111 1011. Okay, so the representation will still be based on what you initialize with. Okay, because the 8-bit value is still the same, whether I put as -5, all right, or I put it in a binary form or I put it in hexadecimal form. Okay, so the operations in this case are all either bitwise or logical, so it makes no difference in this particular example.
Thank you for explaining. Is it the 2 complement representation for
Yes.
the negative numbers that's used in C?
Yes.
Okay. Thank you.
So I can just quickly show you. So 5 is what? 5 is 0 0 0 0 0
101.
0 1 0 1. So the 2's complement means you flip first, so 1 1 1 1 1 0 1 0, and then you add 1 1 1 1 1 1 0 1 1. Okay, so that is your 2's complement representation. Okay, so there was another question of whether we need to know shifting. Yeah, so shifting is again part of your basic operations, which you will actually use also in your assembly language. Okay, so shifting left, shifting right is something you need to know, but I think we're going to cover that very soon in the question later. Okay, so let me move on to the next question here. Okay, so in this next question, okay, we are reviewing the swapping approach. Okay, so in this swapping algorithm or technique, I think what we know is this option, the first option here, where we use a variable, correct? So in this case, we are swapping based on a reference, so it's a pointer. Okay, so what you will do is you will create, okay, what we know is we create a local variable t, okay, and then a is pointing to some value. Okay, so assuming that maybe this is pointing to 5 and this is pointing to 7, correct? So the value that is in 5, I move over to t, correct? The first line. And in the second line, what do I do? Okay, so I'm pointing to another variable, which is b. I take whatever is in b. So if this is 7, I pass it over to a. So it comes here. And then in the last step, I take from t and put it over to b. Okay, so basically whatever a and b are pointing to have now been swapped. All right, so this is the traditional way we know. Okay, but there's another alternative way to do swapping without any additional variable. All right, and it actually involves three what we call exclusive OR operation. This hat symbol here is what we call the exclusive OR operation. So let's just see how this swap works. Okay, so this is how it works, but let's sort of convince ourselves that it actually does work the way they say. All right, so let's put in some values. Okay, so let's just say a. Okay, we're going to put in a value. So 1 0 1 0 1 1 0 0, and I'm going to put in a value for b. Okay, so we're just trying to go through the sequence and confirm that this is really happening. All right, that this algorithm is actually swapping both of them. Okay, so now let's look at the first step. Okay, the first step is this one where I'm doing a exclusive OR with b. Okay, so what is the exclusive OR operation? So let's do that first. So the exclusive OR basically says that, okay, in exclusive OR, the rule is easy to remember. As long as the two bits are different, the output is a 1. Okay, so as long as the two bits are different, the output is a 1. When the two bits are the same, the output is a 0. Alright, so that is the easiest way to remember exclusive OR operation. Okay, so let's go ahead and do this first. So over here, what I'm going to have is the exclusive OR operation, okay, between A and B. All right, so that is the first line. So asterisk A equals to asterisk A exclusive OR with asterisk B. Okay, so let me draw the box here. So what will I get here? So the first bit 0 and 1 is different, so it's a 1. This is 0. This is 1. This is 0. Okay, so again, you just need to look at the two bits. As long as the two bits are different, the output is a 1. If the two bits are the same, the output is a 0. All right, so that is the way in which you can solve this easily. Okay, so I have 1 1 0 0 0 1 0 1. Okay, so I'll call this as the new A from the step 1. Okay, so this is the step 1. This is A step 1. Then let's look at step 2. So in step 2, what is happening? So I'm taking the new A because this A is now going to be used here. Right, the new A, which is from step 1, I'm going to exclusive OR with B. All right, so let's be clear. So this and this, when I did the exclusive OR, I got this answer. All right, now I'm doing this and this exclusive OR, and I'm going to get a different answer here. Okay, so let me put it here. So this two, 1 and 1, I will get 0, 0, 1, 1, 0, 1, 0, 1. Okay, so this is the output of the second line, which is asterisk b is equals to asterisk a exclusive or with asterisk b. Okay, and I'm going to call this the b, the new b from step 2. Okay, so this is the new b from step 2. Okay, and that b, okay, is now going to be used here. Correct. That means now the last step is I'm going to do one more exclusive OR between the a from step 1. Okay, so the a from step 1 is the same a I'm going to use here. Okay, and the b from step 2. Okay, so I'm going to do the exclusive OR one more time. Okay, between these two variables, so 1 and 0 is 1, this is 0, this is 0, this is 1, this will be 0, 1, 1, 1. Okay, so this is basically the final answer here, which is your A step 3. Okay, so this is the last step. All right, asterisk A is equals to asterisk A exclusive or asterisk B. Okay, and now what do you see? You see that this value here is actually, oh sorry, the most significant bit is 0 here. Then 0. Correct, 1 and 1 is 0. So this new A is actually the old B. All right, and the old A is now the new B. All right, so you can see that these three steps, okay, this sequence of exclusive OR operations actually does do a swap, okay, between the two variables without having to incur an additional variable. All right, so that is, I think, the plus point of this approach, okay, compared to the traditional approach that we've been using all the while. Okay, so again, the reason why this question is there is just to give you that idea that even though we may be familiar and very comfortable with a certain approach, and sometimes there can be other techniques which we may not be aware of, right? So sometimes we can look around and we may find that there may be other techniques to writing software or building some hardware that can be better than what we know, all right? Okay, so let's move on to the next question. So in this question, we are going to be looking at this idea of C to MIPS. Okay, C to MIPS. Now, in this question, we are okay. So let's look at the first question first, part A, where B, part A, where we're given that B is equals to A percentage 16. Okay, so this percentage is what? Is the what you call the modulo operator, right? It gives us the remainder. Okay, now before we go into this, let's have a better idea of what exactly we do when we perform this mod operation here. Now let's uh, stick with what we know, our decimal numbers. Okay, and let's just say that we do mod 10. All right, and let me see, we're dealing with decimal numbers. Okay, so if I say that D is equals to, for example, 92, this operation here, what will I actually be doing? I will take 92 divided by 10. All right, and that will give me, okay, that will give me 90, sorry, remainder 2. Okay, 90 remainder 2. Correct. Similarly, if I take a 3-digit number, okay, 157, okay, divided by 10. Okay, if I do a mod 10 operation, again what I will do is I will have to I will get the answer as 150 remainder 7. Okay, so in all these kind of operations, okay, when I do a mod 10, what do? I'm actually extracting the last digit. Correct, that would be the result. Okay, the last digit is the result. So that is why if I take a number that is a multiple of 10, correct, if I take the number as 70 divided by 10, I will get as 7 remainder 0, correct, because the 0 that is here is uh, the remainder after I do the division. Okay, so in all these cases, you can see that the process is that last digit will eventually become the outcome of this operation. Okay, so for a base 10 number, okay, all these numbers here, we are base and decimal numbers, the last digit or every digit goes from, okay, has a range of 0 to 9, correct? It's a 10 different symbols, so it's represented by 0 to 9. Okay, it's represented by 0 to 9. Now in this case here, when we say is percentage 16, okay, when we say percentage 16, all right, you can say that it is actually represented by values ranging from 0 to 50, right? Because 16 different symbols. So you apply the same thinking, okay, as we did earlier. So when we say modulo 10, we know that the range of numbers is from 0 to 9. All right, that is the last digit. So when we say modulo 16, that means the remainder that we expect would be numbers ranging from 0 to 15. So numbers ranging from 0 to 15 means in terms of binary, okay, in terms of binary, okay, it is actually 0, 0, 0, 0 all the way to 1, 1, 1, 1. Okay, if you convert 0 and 15 to the binary representation. Okay, now we can see that A and B are variables mapped to register S0 and S1. Okay, mapped to S0 and S1. That means this is your A, this is your B. Okay, so when I say A percentage 16, all right, the answer that I'm expecting, okay, the remainder I'm expecting is a number that is going to be in the range of 0 to 15. Make sense? Okay, because it's the same thinking as what we saw earlier. When I say modulo 10 or percentage 10, the answer would be a number 0 to 9. Correct? That means that is the remainder after the division. Okay, so the number that we expect is 0 to 9. Similarly, when I say percentage 16, the number that I expect, the answer that I expect is going to be in the range of 0 to 15. All right. So for a 32-bit number, since both S1, all the registers are 32-bit. Okay, so when I look at S0, which is actually A, okay, and I were to represent it in the full 32-bit form, after I do this particular mod operation, I know that the answer that I'm expecting is a number that is between 0 and 15. And this is actually the last 4 digits of my 32-bit number, correct? What is 0, 1, 2, 3. So these last 4 digits are the one, or the last 4 bits are the one that I'm actually interested in, because these last 4 bits represent numbers from 0 to 15. Okay, represent them from 0 to 15. So in order for me to translate this instruction to assembly, okay, all I need to do is I need to take the value of A and I need to only keep the last 4 bits. So to keep the last 4 bits, what do I need to do? I need to do an AND operation with 0x, okay, F. Okay, so the upper bits are going to be 0. So when I say 0xf, means that I want to have another value, another masking value where only the last 4 bits are set to 1 and everything else will be 0. So when I do an AND operation, what I will get as a result is that only the last 4 bits over here. Okay, and the rest will be 0. And this is actually the remainder, correct? Which represents the answer after I do a modulo operation here. So you can see that what we're trying to do is we're trying to think of the most efficient way in which you can translate C to assembly. Okay, and why we need to think this way? Because you want your compiler, all right, when you are writing in C, when you translate it to assembly, you want it to translate into efficient code. All right. Yes, I can do the division, I can do the full operation and then look at the remainder and all of this, correct? But that would be a very inefficient translation. All right. Whereas if I can look at the arrangement of the bits and better understand the operation I'm trying to do, then I can translate it into a very efficient instruction. So as you can see over here, all I need to do is to just perform this one AND operation. Okay, so we know I want to do an AND operation, and this is a AND with immediate value. Okay, this is an AND with the immediate value. So I need to write the instruction now. So the instruction will be AND I. Okay, the instruction will be AND I. And if you remember the format, okay, for AND I, this is the opcode. Okay, then you have your RS, your immediate value, and this will be your RD, your destination. Okay, so if you don't quite remember, then you need to look back at your notes where we talked about the I type and the R type. Okay, to recap the order of the different parts of the instruction. Okay, so the RS would be S0. The immediate value will be 0xf, and the destination will be S1. Okay, so that is basically how you can perform this mod operation very efficiently by just doing a single AND. Okay, by doing a single AND over here. Okay, so of course, when you do an AND operation which is immediate, when you do an operation which is immediate, if you look back at your data sheet, okay, sorry, instruction set. Okay, so this instruction set is there. We need to reference it for some of the instructions, and especially later on when you're doing the instruction and encoding. Okay, so if you haven't downloaded it, please download it from the Luminous. So if you look at this AND immediate instruction over here, you can see that it tells us that RS and with 0 extended immediate. Okay, so 0 extended immediate. So what is 0 extended immediate mean? So if you look back at your format, okay, your immediate value, if you recall, we say that it occupies the lower 16 bits of the instruction. So 0 to 15 is your lower 16 bits. So when I specify, okay, when I specify in my instruction that it is going to be 0xf, okay, so in this instruction it is written as 0xf. Okay, so I'm only specifying the lower 4 bits here, 1111. All right, but rightfully I can specify the full 16 bits. Okay, but if you don't specify also, this is equivalent Okay, this is equivalent to writing it as 0x000f. Okay, so it will be 0 all the way here. Okay, but this is only the 16 bits. How about the upper 16 bits? So that is where the what they said comes into play, which is the 0 extended. Okay, so looking at the instruction, and immediate will give a 0 extended immediate. So this 0 extend immediate, what it means is it will automatically extend by putting in zeros for you at the upper 16 bits here. Okay, so effectively it is full 32 bits, all right, but only the lower 4 bits in this case are being set to 1. Okay, so we will be looking at more into the behavior of the processor and how this extension and all this comes into play. Okay, when we are looking at the data path and control chapters later on. Okay, but this gives you an idea what is happening when you write an instruction. So when you write an instruction, okay, you are telling the processor to carry out some activity, okay, but the processor still needs to interpret the instruction correctly. Okay, so that is where the instruction format comes into play. Okay, so we will be looking at this again, okay, in the next chapter when we're looking at the encoding part. Okay, so that is only the first question here, part A, B and A percentage 16. Now let's look at the second question here. In the second question here is B, A divided by 8 and then multiply by 8. Okay, so let's look at this. Okay, let me shift this down first. Okay, so let's look at the second part here. Okay, so in part B, your question is B is equals to A divided by 8 multiplied by 8. Okay, so this is where somebody asked about the shifting operations. Okay, so this is where the logical shifting actually helps us a lot. All right, so if you remember, okay, so if I take a 4-bit value 0001, and if I shift left, take this and I shift left by 1, the result will be 0010, correct? If I shift left by one more time, okay, then the result will be 0100. If I look at it in terms of decimal value, this is 1, this is 2, this is 4, and so on. All right, so what we know is whenever I shift left, okay, it is equivalent to multiply by 2, multiply by 2. All right, when I shift right is equivalent to divide by 2. Okay, so it's always 2 power something, correct? So if you imagine that if I one shot do logical shift left 2, okay, that means if I take 0001 and I say shift left by 2, it will be 0100. Okay, so that is equivalent to multiply by 2 to the power of 2. If I shift left by 3, it will become 2 to the power of 3 and so on. Okay, so every time multiplying by 2 whenever you shift left, dividing by 2 whenever you shift right. Okay, and why is this important? Because this allows the compiler to replace multiplication and division operations with equivalent shift operations followed by another add operation. Okay, in the case of, let's say, an odd number. And again, why is this very important? Because you want to optimize the final assembly language code to run as efficiently as you can. Okay, even though your processor may support multiplication and division operations, okay, they are considered very computationally intensive operations because it takes a lot of clock cycles to complete. Okay, whereas if I can replace those instructions with shift operations, they are a far more efficient way of performing the same kind of or achieving the same outcome. Okay, so that is why the compiler plays a big part, all right, because you want the compiler to be smart enough, all right, to translate your C code to efficient assembly language code. Okay, so with that understanding, okay, so let me just summarize here. So this is basically shifting right by 3. Okay, and this part here is shifting left by 3. Okay, so let's put some numbers, okay, and see what happens. So let's assume that my binary number, okay, is maybe 110000 something, okay, and let's say the last 4 bits are 1111, okay. So let's say this is my number I'm starting off with, and I say I do the first operation, which is shift right by 3. That means this will come 1, 2, 3, right? It will go 3 bits. Okay, so this 1 will come here, so this 1, and what gets shifted in will be 0. So I'll have 3 zeros in front here. Okay, and everything else will get shifted. So this 1 will come here, and I get a 1 over here, and this last 3 bits here will get shifted out. Okay, so that is what will happen when I do the first shifting. Okay, I do the first shifting. Now the next one is shift left by 3. Right, next case I'm going to shift left by 3. So when I shift left by 3, what is going to happen? So I'm going to shift this back. So it's 1, 1. So this 1 was shifted here, correct? So that 1 will come back. So 1, 1, 0, 0, and all the other bits in between. And this 1 will now come back here. So 1. All right. But the last 3 bits, what will happen? Okay, since these 3 bits were already shifted out, okay, they're considered out of the register already. You can't get them back. So what gets shifted in is 3 zeros. Okay, so technically what this is doing, yeah, shifted out means it's gone. Okay, it does not get shifted to some other decimal or some other place. No, once you shift out, it's considered it's gone. All right, so technically what you're doing here, okay, what this operation is doing is actually clearing the last 3 bits. Okay, so you can see that by doing this operation, I'm actually clearing the last 3 bits of my register value. Yeah, so this is considered a integer division. Okay, so what we're trying to show you here is the way the compiler, okay, will try to interpret division and multiplication instructions so that it is more efficient for the execution to carry out. Okay, now this is equivalent, correct? So technically what we're trying to do, we're trying to clear the last 3 bits, correct? We're trying to clear the last 3 bits. And we just saw that this technique here, where I can do an AND operation, okay, with a ones, that means I keep the bit, and we know that if I do an AND operation with a 0, I clear the bit, correct? I clear the bit. So why can't I do something like this? Okay, why can't I say that okay, so shift is generally used for multiplication and division, okay, and shift is of course Okay, so shift is generally used multiplication division, and we use it extensively when we want to maybe extract out certain bits to certain positions in a register. Okay, currently we are dealing with the information as just ones and zeros, correct? But in the processor level, sometimes you will look at it as groups of bits or individual bits that represent some information, and you may want to shift that information to specific locations only in that particular register. Okay, so maybe you have some data in bit 0 to 3. Okay, so for example, you have some data. Okay, this is 32 bit. I have some data in 0 to 3, but I want this data to come to 7 to 4. Okay, because I need it to be in that particular location for the operation to carry out. Then I can just say I want to do a shift. So in this case, you are not shifting because you are thinking of it as a multiplication, but you are shifting because you want the data to be in a particular position before the next operation is carried out. Okay, or the data passes through the next part of the processor and so on. Okay, yeah, so when we are looking at the data part and control part of it, we will sort of see why we want certain bits in certain position. Okay, float is not something we are covering in this module. If you look in your instruction set, there are floating point instructions over here. But again, this is not a full-fledged assembly language module. Okay, so if you were to go to all of that, then I think we can't cover anything else in this module. Okay, so it does support, okay, MIPS does support, almost all processors support all these operations, but for us, we are already going to be focused only on this. Yeah, correct. We still have a lot to learn, correct, and still got some more coming. Okay, so coming back to my question just now, so we know that I want to clear the last 3 bits, all right, of the information inside register S0, all right. A is in S0, so this is S0, and I want to write it to S1. Okay, why can't I just do an AND operation? Okay, why can't I just say, okay, S0 have some data, and I do AND, okay, do an AND with immediate value, where the value that I want to do an AND operation is such that the last 3 bits are 0. So if the last 3 bits are 0, okay, you can say that is okay, so let me just write the last 3 bits here, and everything else is 1. Okay, can I just do an AND operation like this, and then I get the final answer here?
No, I think you cannot do that.
Any reason why?
I think it's because you do not know what's the remainder beforehand. The size of the remainder can be different for different input.
Okay, so in this case, we were not doing a remainder, but we are just thinking of it as an AND operation, correct? Because my idea is I want the last 3 bits here to be clear, all right? So if whatever is the last 3 bits here, if I do an AND with a 0, I'm guaranteeing that the last 3 bits will become 0 here.
Like bit masking.
Yes,
bit
correct.
Masking.
Correct. So
Yeah, then that's fine.
the bit masking technique, correct? So we have seen this before. Now, this idea, of course, is correct. There's nothing wrong with the idea. Okay. The issue why we can't write an instruction like this. Okay, that means technically, if I were to write an instruction, and I S0, so this value here, okay, this value here will be represented as 0x f f f f f f f8. Okay, and put into S1. Okay, why F8 is because hexadecimal is everything is always represented in 4 bit, correct? So the last 4 bit is 1000, so that is 8. So this is how your instruction would look like. Okay, because if I do an AND operation of S0 with this particular mask, that means all ones. Okay, all the upper bits are ones, so it's all F, and the last hex is 1000. Okay, because the last three bits are 0, but everything else is 1. Okay, so theoretically this is how the instruction would look like. Okay, but why is this not possible? Why can't I just solve it with this one instruction here? Okay, so the reason why we can't do this, okay, the reason why we can't do this, again, it comes back to the instruction format limitation. So if you remember this, what we saw just now, immediate value has a limitation of lower 16 bits only. It's lower 16 bits only. That means I cannot specify a full 32-bit value. This is a full 32-bit value, which is not allowed. Correct? I can only specify 16 bits. Okay? So in order for me to load a 32-bit value into a register, okay? Okay? In order for me to load a full 32-bit register, what I need to do is I need to break up the instruction, break up the data into separate instructions that will load the upper 16-bit and then the lower 16-bit. Okay, so this was actually in one of the slides. Okay, in your handout. Okay, so the steps you need to do. Okay, the steps you need to do is you need to do a load upper immediate first. Okay, into a register. So I say T0 with 0xFFFF. Okay, when you do this, what will happen? That means inside register T0, I will take the upper 16 bits and I'll put in a value of 0xFFFF. Okay, then I need to do a OR operation, or immediate T. Okay, I can use S0 here. S0 T0 with sorry, let me use T0 here. T0 with 0xFFF8. Okay, so what does this do? This, as you can see, is only a 16-bit value. So I will take T0, I will do an OR operation with an immediate value of FFF8. So when I take a FFF8, okay, and what it will do is it will automatically extend it to zeros in front. So when I do an OR operation, what will happen? Anything OR with 0 does not change, correct? So the final answer here will be FFFF and FFF8. Okay, so when you do a load upper immediate, you will also make sure that the lower bits are all 0. Okay, so you need to break up your 32-bit data into 2 separate instructions, and then you will get the final value in that register. So currently, after I do these 2 instructions, then your T0, okay, the T0 will be loaded with the correct value. Okay, so you don't need to copy or it anywhere else. You just need to make sure that, okay, you know that this is the data I want, correct? This 32-bit data is the data I want. So you need to sort of split it up into 2 parts. Okay, FFFF and FFF8, and perform these 2 instructions. That means in the first instruction, you take the upper 16 bits and put it into one register, and then you do a OR with the lower 16 bits. Okay, so you're not storing it anywhere else, but you just have to do these 2 instructions to make sure that at the end of these 2 instructions, your register, in this case T0, is loaded with the full 32-bit value. Okay, and then I can do the final instruction, which is to AND my S0 with T0, okay, and then put it into S1. Okay, so this is the other way in which you can achieve the same outcome. That means I want to clear the last 3 bits of the data in my register before I or this equivalent to this particular shift operation that we just saw. Okay, so it takes some time. Okay, right now if you're still a bit unfamiliar with some of these instructions, it is fine, all right, but you need to definitely read up, okay, and get familiarized so you understand, okay, how these instructions work and what we are trying to do. Okay, so let me go to the last question for the tutorial. Okay, so in this question we are looking at this example here where this code, okay, is addressing some content in memory. Okay, it's addressing some content in memory. So let's look at it step by step and try to figure out what is happening. Okay, so we have 2 registers, S1. Okay, so we have 2 registers here, S1, and another register here, T0. And inside the code, I'm using another register, T1. Okay, so S1 is originally loaded with the value of 0, and T0 is initialized to 1, 1, 2. Okay, so let's go through what is going to happen while I am executing this code here. Okay, so the first step is, okay, so let's go to line by line. So the first line, BEQ T00, that means I'm trying to check whether the register T0 is having a value of 0. If it is true, I will branch to the exit label. So in this case, I will not branch because T0 has a value of 112. So that's the value of 112. Now let's look at the next line. Okay, in the next line, this is what a load word instruction. So load word, okay, is to read from memory. Okay, so if you recall, load word T1 0 T0. Okay, what does this instruction do? Okay, so let's quickly look at this. So in this instruction, T0 is holding what? Okay, T0 is holding the address. Okay, uh, okay, or we can put it as T0 is pointing to an address location, pointing to an address. Okay, and this is the offset. Okay, so T0 is pointing to an address, and from that address I add an offset. Okay, and after I do this addition, this is the final address where I access the data. Okay, so this is the final address where I access the data, and I take this data and I put it into T1. Okay, so I take the data and put it into T1. So that is what your load word is doing. That means your whatever is in your bracket that is pointing to an address, I add with the offset, then that is our final address. I go to the address, I take that data and put it into T1. Okay, so that is what load word is doing. Okay, so now coming back here, we can say that T0 is pointing to address location 112. Correct, that is where T0 is pointing to. And I add an offset of 0, that means there is no offset. So I take the data that is currently in this address location, which is 108, and I put it into T1. That means 108 comes here. Okay, 108 comes here. So that is that second line over there. In the third line, okay, in the third line, what is happening? I do a add. So this one is quite easy. Add S1 with T1, put back into S1. So S1 add with T1. So 0 plus 108. So 0 plus 108, I will get 108. So I replace this with 108. Okay. And then in the last line, in the fourth line, I say load word T0 plus 4. Okay, so it is similar to the earlier line, except that now I have an offset of 4. So T0 is pointing to, T0 is currently pointing to address location 112. I add an offset, so it becomes 116. So this plus 4 will point to the next address. And then I take the data in that address, which is 124. Okay, I take the data in that address, okay, and I put it into T0. So the value of 124 comes into T0. Okay, and then I jump to loop. Okay, so what we have done is the first iteration. But after this, I jump back to the loop. All right, so that is the first iteration of the loop. Okay, we are supposed to execute it for 3 iterations and tell the final value of register S1. Okay, final value of register S1. So let's look at this. Okay, now let's go to the second iteration. Okay, so in the second iteration, again, we start off with the check. The check is T00, it is not 0, so I do not exit. Okay, so let me erase this. Okay, and start again here. So I come back here again, I load. So now where is T0 pointing to? Okay, now T0 is holding a value of 124, so I'm pointing here. Okay, so T0 is holding a value of 124, so I'm pointing here. And I add an offset of 0. Okay, so I do not go anywhere, so I stay there. And I take that data in address location 124, which is 104, and I put it into T1. So this one will become 104. Okay, then I do the next step, which is to do an addition of S1 with T1. So now I'm going to take 108 plus 104. Okay, so 108 plus 104 will be 212. Okay, 212, and I'm going to put it back inside here, so we'll get 212. All right, and then the next line here, okay, is another load word. So I look at wherever I'm pointing, T0 is pointing to, and I add an offset of 4. So I add offset of 4, which is 1 to 4 become 1 to 8. I take the data there, which is 100, okay, and put it into T0. So from the new data here will be 100. Okay, and then I jump back to loop. Okay, so that is the completion of the second iteration. Okay, and then let's do the last iteration. So at the start of the last iteration, I checked, is T00? No, so I do not exit. Okay, so where am I pointing to now? Okay, so now T0 is pointing to 100, which is here. Okay, so the T0 is pointing here. And I take the data, the T0 is pointing to, okay, offset of 0, so I don't go anywhere. I take this data, okay, and I put it into T1. So T1 is now going to have a value of 120. Okay, so that is this line over here. And then I do an addition with what I have here. So 212. So 212 plus 120, I'll get 332. Okay, so the value inside here would be 332. Okay, and then the next step would be to go back to T0, but now I add an offset of 4 plus 4. Okay, and that will give me 104. Correct, and I take the data in that address location and I put it into T0. So the value here will become 132. Okay, and then I jump back to loop. Okay, so now we have completed all 3 iterations. All right, so we complete all 3 iterations, and the answer for part A over here, give the value of register S1 at the end of the 3rd iteration. Okay, so the value of S1 at end of the 3rd iteration is this 332. Correct, I've completed 3 iterations and the value inside register S1 is 332. Okay, now over here in part B, they're asking us if you want to terminate the loop at the 4th check. Okay, that means right now. Okay, because I've done 3 iterations and I'm starting my 4th iteration. So in the 4th iteration, okay, when I'm checking my BEQ, I want to terminate the loop. So what must I do? So in order for me to terminate the loop, what is the condition? The register T0 must hold a value of 0. Correct? Must hold a value of 0. And what is the last value I loaded into T0? The last value I loaded was the content of address location 104. Okay, was the content of address location 104. So if the content of 104 was replaced, okay, if this was replaced with 0, then what happened? That means instead of 132, I would have gotten a 0. So when I start the 4th iteration, this condition would have been true and I would have branched to exit. Okay, I would have branched to exit. Okay, so that is basically what this question is about. So in this question, basically it is a way, it's a good starting point for you to make sure you understand the concepts of the different type of instructions, your branch instruction, your jump instruction, your load word, okay, and your add. Okay, and of course for load word and store word, you must understand a very important concept, correct, that the register that we are specifying in the bracket is actually holding information about the address location I'm pointing to. Okay, the address location I'm pointing to, and then I take that information, I add with the offset. Okay, so this concept over here is very important. Okay, so you understand how to interpret this instruction correctly. Okay, T0 is pointing to an address, I add it with the offset, and then I finally go to this address location and I access this data and I move this data to a register. Okay, to a register. So that is what is this question all about. Okay, so I know it's quite a lot of stuff we covered, all right, but I think it sort of gives you the idea of that you need to make sure you are familiar with all of this stuff, correct? Your IEEE programming, more or less, you're comfortable, but assembly language is something new and something different, okay? So you have to get familiarized with some of these instructions, the formats, okay, how it works and so on, and then you sort of see how all this comes together. Okay, so what I will do now is I will run through the Qt stream first. Okay, so basically now we wrap up the tutorial. Any questions that anybody have regarding the tutorial questions? Okay, probably you'll have more questions, okay, as you start to revise it, you know, and you start to go through. Okay, but all this will be uploaded, correct? So you can always look back at these videos to understand what is happening. Okay, so let me open up the Qt stream. So you can see how some of these can be easily tested, okay, with your own assembly language code. Okay, so when you open up the Qt stream, okay, like what you see here, it's a very simple interface, very lightweight. Okay, there is a text segment and a data segment. Okay, so a text segment is where you load your code, and data is where you can see the information that you are currently processing. And on the left hand side, the column over here is where you can see all your register information. Okay, in order for you to write code, okay, you need to open up in terms of a ASM file. Okay, so you can use any simple text editor, okay, like WordPad or Notepad, okay, to write your code. So when you write your code, there are certain things that you need to add in before and after. All right, so that's where I want to show you the demo over here, so you can sort of see what is happening. All right, so in this first example here, it is just a single line of code. Okay, add I 0 with 97 put into T1. Okay, so effectively what I'm trying to do is I'm trying to load a value of 97 into T1, but in order for me to load that, I need to add with 0. Okay, so that is what this instruction is doing. But the line before that is important, the dot text. So this dot text is for us to tell this system that this is a piece of code that is supposed to be loaded in the text segment of your memory. And then there is this load immediate bi 10 syscall. Right, so these instructions are actually specified inside your assignment document. So if you look inside your assignment document, okay, that I've uploaded, okay, you can see that this instructions here, which is syscall, are what you call system level calls. And when you load your V0 register with specific values, it actually triggers certain actions. So if I load V0 with 10, okay, that means it is equivalent to say I want to exit. That means that's it, that's the end of the program. Okay, so you don't need to worry so much. Whatever is needed is sort of explained quite clearly in the assignment handout. Okay, but what I want to show you is how do you run this code. Okay, so now after you have written your code and you save it as a .asm file, okay, you can come inside your Qt stream and you can open up. So you go to file, you load file. Okay, so it's not like a normal C programming kind of environment where you can directly write your code and everything. So you need to load your ASM file. Okay, so okay, so this is your sample one ASM. Okay, so you can see that once you load, okay, it translates that code to the actual assembly language, and your registers that you choose. For example, you choose T1, okay, but it will represent your register names with the actual register numbers. Okay, so T1 is actually register 9. Okay, and then the other instructions here are to do the system call. Okay, the V0 and syscall. So that part you don't need to worry so much. We just look at the first instruction here, add I. Okay, to run, you click on the play button here. So it will run, and when it runs, okay, you will see that, okay, it is changing some register values. In our case, okay, what we are interested in is what did we try to do? We tried to load register T1, okay, with a value of 97. So if I come here, if I zoom in, I can't zoom in so much here, but if you look here, register T1 has a value of 61 over here. All right, so is it correct? I tried to put 97 here, but I put a 61 here. All right, the reason is because inside here, okay, all the values are represented in hexadecimal. Okay, so if you use your calculator here and you key in 97, you'll see that it's actually hex, it is hex 61. Okay, so that is what is happening here. Okay, let me just quickly show you another one. All right, so one of the important things to remember is whenever you want to change code, okay, you want to run some changes, you need to change your ASM file. And over here, okay, what you need to do is you need to make sure you go to simulator and you click on Re-Initialize Simulator. Okay, so you need to Re-Initialize Simulator first. That will make sure it clears off all the data from the previous run, and then you load again. Okay, so in this case, let me load sample2. Okay, so let me open up the sample2 file over here. Okay, so in sample2, basically what we are doing is we are having a data. Okay, so this data has two parts to it. One is the actual hexadecimal value. The other one is the ASCII string. Okay, so if you click from the text tab, you click on the data tab. Okay, you can see that there is actually this data over here. All right, so this data over here is starting, okay, from this address location. So this data is saying that I'm going to start from this address location 100000100, and the data that is starting that I'm putting in this place is this ASCII string called hello, HELLO. So we can see it over here. All right, so in this case, what is happening is you are putting in data inside the data segment of your program, and you can access that data later on. Okay, this code is not doing anything much. Okay, but if you look at it, V04, okay, if you look back at your assignment, V04 is to print string. Okay, so when you put a V0, load V0 with a 4 and you do a syscall, you're actually printing the string. So what is happening? So you can see over here that I actually have a console. So if I run this code now, it will print hello to the console here. Okay, so that is what this is doing. All right, so you can roughly get the idea of how to write your code, okay, through this. The important thing is, okay, you will get more experience when you look at the lab manual. You have a data segment and you have a text segment. The text segment is where you write the actual code, okay, what you want to do. Okay, the syscalls are tied with the values you load in specific registers. Okay, so when I want to print a message, for example, I need to load the address of the message into a particular register, and then I have to call syscall. When I want to exit, I need to load a value in a particular register and then do syscall. Okay, so those important ones are specified in the lab document, which you can try. Okay, so it is quite a fairly easy and doable assignment. All right, it's just some practice of some of your assembly language code only. Okay, and it also gives you a good sort of framework for you to test out your assembly language and practice and get better at it. Okay, so that is just what I wanted to show you. Okay, in terms of the Qt stream. Okay, you can look through the assignment first. Okay, we have about, I think, exactly about a month, okay, to submit it. Okay, so you have more than enough time. You can look through and then you can start to play around with the Qt stream and get familiarized first, and then start on the assignment. Okay, so now it's going to be 8 o'clock. Okay, let's have a break now. Okay, let's have a break, and then I will see you back here in about 20 minutes time. Okay, now about 8:20. Okay, and then we can start the next chapter, okay, on the instruction set format. Okay, so I will see you all back here, okay, in 20 minutes time. Thank you. Okay, so let's carry on, okay, with our lecture now. Okay, so let me share the screen and yeah, recording is on by default, okay, for all the sessions. So Okay, so let's get started here. So in this lecture, we're going to be looking at the instruction formats and encoding. Okay, that means uh, how do we structure the instructions in a particular format and encode the important information that we need. All right, and this is important as you will see later on when we're looking at the data part and control of a processor. Why certain bits have to be in certain positions? Okay, because the hardware side, okay, the processor side, certain things are already hardwired, okay, to perform certain actions in a particular way. So it is important that the ordering of the information, the bits, all of this plays a part. Okay, so we will look at some of these examples. Now, so what we know is we have seen that we start off with high level language, okay, for example, C, all right, and then we can translate that to assembly language, which is, of course, more relatable with the hardware that is underlying. Okay, so when you write an instruction that moves data between registers, moves immediate value into a register, performs an add or a shift or something, we sort of relate that closer to the hardware that we are dealing with. Okay, but in terms of shifting, all right, we have, or in terms of some of the things that we saw, like immediate value, all right, we say that it's only limited to, for example, 16 bits. When we're talking about shift, we only have 5 bits and so on. So there are some limitations or some standards that we need to conform to when we are following a certain processor architecture. All right, so different processor architectures may will have different rules and different designs. Okay, so in MIPS, we have the process that we are studying, we are going to be following their own sort of framework. Okay, so the first thing is we know that all our registers are 32 bits, all right, and all our instructions are also having a fixed length of 32 bits. Okay, and what does that tell us? That means all the operations that I want to carry out, okay, have to be uh, sort of represented within the 32 bits. Okay, so if you look at your instruction set, okay, you see there are so many instructions, so many variations to those instructions, but I need to make sure that all of those instructions are represented within this 32 bits. Okay, and the idea is you want to keep reusing that same hardware that you have built again and again for as much of the instructions or as many of the instructions as you can. All right, and that allows your hardware design to be minimized. All right, you do not want to create separate copies of hardware just because you want to have something slightly different. Okay, so for example, add operation. Correct, if I say I have an add operation, I can say uh, T0, T1, and T2, for example. This is a add operation between two registers, and the result I put back another register. At the same time, I also we also know that there is an add I instruction where I can say T1 add with 5, put back into T0. Okay, so as you can see, both are similar instructions, except that except that one is dealing with both operands from registers, the other one is one register, one immediate. Okay, but we want to make sure that the design of the processor is such that with as minimal change as possible, I want to be able to support all these type of instructions instead of trying to say one block is specifically for add, another block is specifically for add I. So that would be a waste of resources. Okay. So in terms of instructions format, there are basically 3 types. The first one is the R type, okay, where all the source and destination are specified in registers. The other is the I type. So the I type, what we have been seeing is the type where we have a arithmetic or logical operation with an immediate value. The load word and store word are also considered R-type instructions because they deal with register and an immediate value, which is the offset. And your branch instructions are also classified as R-type. Okay, so when you say branch is equal, branch is not equal, they are also classified as I-type instructions. Okay, so you will see how and why that is actually important. Okay, the J format is the jump instruction. There's only one, which is jump to a particular address location. Okay, so even the R-type instructions, even though we say that you have two source and one destination, there are some special cases, especially with the shift operations, again, which we will go through in a while. Okay, the MIPS has 32 registers, okay, as we have seen, and the 32 registers can be sort of accessed using their name, okay, or using the number. As you saw in Qt's PIM, when I put it in the name, it will still translate into the appropriate register number once it gets loaded. Okay, but that is fine. Okay, when you're writing the code, you can still stick to your naming using the names in your code. Okay, so let's look at the R format instruction first. So the R format instruction, the 32 bits is broken up into this. Okay, 6 plus 5 plus 5 plus 5 plus 6. So this basically breaks down the instruction into a 32-bit instruction into different parts. Okay, and each field has a name. Okay, the opcode, RS, RT, RD, shift amount, and function. So when you say I have a 5-bit field, okay, which is RS, RT, and RD, it tells me that the 5 bits can be used to represent numbers ranging from 0 to 31. Okay, which is basically the 32 registers that we have. Correct? Because since the RTA instruction is referencing 2 registers to get the information, I need to make sure I can specify all the 32 different registers. Okay, so that is why 5 bits is just nice to represent the registers. Correct? So when I put a value here, for example, 00001, then that means I'm talking about register 1, the data inside register 1, and so on. The 6-bit field, okay, can represent numbers from 0 to 63. There is a total of 64 different symbols or values. Okay, and that is used in both the opcode and the function field. So that basically specifies the different parts of the instruction for the R format. Now let's look at this. This is a add instruction, and this is what we call a R type instruction or R format instruction. Why? Because all of the registers are specified, sorry, all the 3 parameters are specified as registers. Okay. Now, when I look at this instruction, the first thing is, okay, you automatically know that this is your RS, this is your RT, and this is your RD. Okay, RS, RT, and RD. Now, so when coming back here, out of the full 32 bits, this 15 bits you already know. Correct? If it is not a shift instruction, then the shift amount will be 0. Okay, all these 5 bits will be 0. Okay, so that is what is shown here. Okay, now the only thing left is the opcode and function field. Correct? Opcode and function field. Okay, so how do I figure out this 6 bits and this 6 bits over here? Okay, so that is where your instruction set comes in. Okay, so let's look at your instruction set here. So if you open up your instruction set, if you look at your add instruction for R type format, okay, so the format here, the first one here is R. So it's RS, RT into RD. the last column here gives you opcode / function field. Okay, so the first number here is what we call the opcode. The second number here is the function field. Okay, this is given in terms of hexadecimal. Okay, it's given in terms of hexadecimal. For some instructions, you can see that there is no slash. That means there's only one field, and that field is the opcode. Okay, in some instruction, you have the opcode and function field. Okay, so in this instruction, add, you can see that the opcode is 0, the function field is hex 20. Okay, now let's bring that back over here. So what we know is the opcode is 0. Okay, the opcode here is 0, and the function field is hex 20. So 0x20, if you key in your calculator, you translate it, you get a value of 32. Okay, so that is how you get this representation here inside the instruction. So over here, what you have is your add instruction. Okay, in this add instruction, you have your register. Okay, RS, RT, and RD. So this is your RS, RT, and RD. So these go into these locations. And like I said just now, if it's not a shift instruction, your shift amount will be 0. And the opcode and function field are given from the instruction set. Okay. Now, to translate that into binary, okay, you will get this. Okay, and of course, from there you can also represent it in the hexadecimal. When you represent it in hexadecimal, you don't worry about the number of bits used to represent different parts of the instruction anymore, because you just do the normal approach, which is group it in terms of 4 bits and 4 bits and so on. Okay, so that doesn't matter that it cuts across different fields. Okay, what we are just trying to do is have a more easier way of representing the ones and zeros, correct? Because if you just see all ones and zeros, is quite difficult to interpret it, but in hexadecimal it's a bit easier to see. Okay, so let's look at this shift instruction. This is so shift instructions are a bit different. Okay, so for shift instructions, what you have is you have your RT and RD. Your RS is 0. Okay, so this is something unique for the shift instructions alone. Okay, so this is your RT. Okay, this is your shift amount, and this is your RD. Okay, and there is, okay, so if you look at shift left in your instruction set summary, okay, you will see the SLL, your opcode is 0 and your function field is also 0. Okay, 0 and 0. So that is why over here you get opcode is also 0 and function field is also 0. Okay, that is from the instruction set. All right. So of course, right now you may think, okay, why do we choose RT to be 9? I mean, why do we choose RT to hold the value or the register the information? Why didn't I choose RS? Since RS is also available. Okay. So all of this again ties back to the design of the hardware later on. Okay, so there are very valid reasons why the format and the positioning of the different registers and bits is chosen this way, because we want to create a structure, a hardware structure that can easily extend to support all these different instructions. Okay, so when we are looking at that later on, you will come back and you can see the reasoning behind why the RT is chosen, why RD is chosen this way, and so on. Okay, so you will see that appreciation later on. Okay, so this is another example. Okay, so I think you already have the answer there, but let's go through the steps. Okay, so the first step is you have RS here, you have RT, and this RD. Okay, so what you need to do is you need to translate each of this into 5-bit, okay, 5-bit values. So that is here. Okay, so okay, now we are just putting the values here, RS, RT, and RD. Okay, so again you notice that there is a difference in the order. When you write the instruction, your RD comes first, but an RS, RT comes later. But in the representation, your RS comes after, of course, RS, RT, and then RD. Okay, so again, you must understand there is a difference in the order between the instruction writing and the representation in the actual binary format. Okay, so that will be the final value here. All right, so far you can see it's quite straightforward. You take the instruction and you represent it in the correct locations in that 32-bit instruction, and once you can do that, you can then do the translation to binary and then finally hexadecimal. Okay, so in terms of, okay, so that is for R-type instruction. For I-type instructions, okay, what are the things that we need to look at? So the first thing is for shift instructions, the support is up to only 5-bit shift amount. Okay, so you can only specify the shift amount within 5 bits. So I can, at most, I can shift up to 31 bits. All right, and that should be all that you need, because when you shift up to 31 bits, basically you already shift everything. All right, because the whole register is 32 bits only. Okay, so you do not need any more bits to do any shifting. All right, but in terms of other instructions, okay, your immediate value, you might want to have more. Correct. Now, how do I stick with the current instruction format which I've already designed for R and extend it to represent I? Okay, so if I come back here, you can see that when I want to do R I type instructions, I only need 2 registers and I need an immediate value. Correct. So how much space do I have? Okay, since I only need opcode and 2 registers, I have all these 3 amount of register or bits available for me to use. Okay, the opcode is always there. If you look at all the instructions, the opcode is a compulsory element of any instruction, because you need to tell the processor what you're trying to do. Correct. So that information is contained within the opcode, and in some cases you have the function field also to have a further breakdown. Okay, but without the function field, you still need the opcode, because the processor needs to know what it is supposed to do with the rest of the bits. Okay, so you can see that now I already have this idea, this framework for R-type instruction, and I want to extend this idea to support I-type instructions. So for I-type, we know that I need opcode, I need 2 registers, correct? And then I need the immediate value. Since opcode is fixed, registers, the sizes are fixed. Okay, so opcode is 6 bits, this is 5 and 5. That means 16 bits I need. Correct. That means I now have another 16 bits that are freed up for me to hold the immediate value. Okay, so that is the thinking behind how this format comes about. Okay, so the first 16 bits is the opcode plus RS and RT, and then the remaining 16 bits is for the immediate value. Okay, so that tells us why we are limited to 16 bits, because I don't have any more space left. All right, I need 6 bits for opcode, I need 5 bits each to represent the other 2 registers. Okay, so out of the 32 bits, 16 bits are already used up, so I only have 16 bits left. So that is why we said earlier that for I-type instructions, the immediate value is limited to 16 bits. Okay. So interestingly, also you must understand that you have RS and RT. Okay. Then you do not have RD anymore because you only have two registers. Okay, and the rest of it is the immediate value. Okay, in terms of naming convention, previously, okay, if you look back here, okay, we said that both RS and RT were considered the source registers, okay, and RD was considered a destination register. Okay, so that was in R type. But now that we are moving to only two registers, okay, we are saying the RS is the source. The RS is the source. Okay, and RT is the destination. Okay, this is the destination, and this is the source. All right. So this again has a reasoning behind it. Okay, why we never use RD? Okay, why we use RT? Okay, so there is a reasoning behind this because it ties in with the design of the hardware. All right, so for I-type instructions, you have RS, RT to get an opcode and the 16-bit immediate value. Now, this 16-bit immediate value that is specified is represented as a signed integer. So when you say signed, it means what? That means it is a value that has both positive and negative representation, and it is using the 2's complement form of representation. Okay, so that is something that we will look at in a while as well to better understand how to interpret this signed integer. Okay, so now let's look at this example. Add I 21, 22, and negative 50. Okay, so the first thing is we know that this is your RS, we know this is your RT, and this is your immediate. Okay, now for I-type instructions, all right, you don't have any function field anymore. You only have opcode. So the opcode we can extract that from the instruction set. Okay, so add I, okay, add immediate, you can see it is opcode is 8. Okay, opcode is 8. Okay, so let's come back here. So that is how you get the opcode value here as 8. Okay, RS and RT is given and the immediate value is also given. Okay, so in the instruction here, we have specified immediate value as negative 50 in our normal decimal representation. Now let's see how we can put that in the instruction. Okay, so first is of course the opcode. Okay, this is the opcode 8, then followed by RS and RT. Okay, so the next step is the interesting part. 8, 22, and 21, no problem. We can directly translate. Negative 50, again, we need to make sure we represent it in the correct form. Again, this is 2's complement. So let me just bring up the calculator again, just so that we can see the link. Okay, so for 50, the negative of it is again 16 bits. So if you look at the 16 bits here is 8 ones over here, then 1100, 1110, which is also what you have here. 8 ones, then 1100, 1110. Okay, so that is what I mentioned just now, that the immediate value is represented as a 2's complement sign bit. Okay, 2's complement sign bit. Okay, how about load word instruction? So a load word instruction, okay, what it does is it, again, you have your RS here, you also have your RT here, and you have your immediate value here. All right, so even though we write the instruction, the way we write the load word instruction is of course very different from how we write the add-I instruction. All right, because here you can specifically see that the immediate value is separated, whereas here the immediate value is sort of more intertwined with the instruction. Okay, but that is just the assembly language code. Okay, but in terms of translation, okay, to the binary, it is still the same. Okay, you have your opcode, okay, your RS, RT, and your immediate. Okay, so again, opcode, we can always look back at your instruction set to know what is the opcode. Okay, so that part I'll leave it to you to have a look. All right, I've been showing you how to do it. Just need to look at the instruction set and relate it back to the opcode field that they given. Now this immediate value and opcode you then translate, and then you will get this. Okay, so you can see it's not so difficult. Okay, once you get the hang of it, you more or less understand how to relate instructions in the assembly language format to the actual representation in the different fields in the 32-bit instruction, and then from there you translate to hexadecimal, binary and hexadecimal. Okay, so that is of course your basic instructions, your R type and I type. Now, of course, there are other instructions as well. Now, one of the important registers in the processor is what we call the program counter. Okay, so it keeps track of where you are in the execution of your code. Okay, and that is important, correct? Because you don't always go in sequence, correct? You have branch instruction, you have jump. Okay, so when you have this kind of conditional statements in your code, you can suddenly jump to some other location somewhere else. Okay, so we need to be able to keep track of where we are and what we're going to execute next. Okay, so in terms of branch instructions are also classified as I-type instructions. Okay, where your opcode here, okay, has two options. One is BEQ and BNE, and then you specify the two registers you want to compare. All right, when you say BEQ means you are comparing two registers, same as BNE. Okay, now here the immediate value that is specified, we said just now, is only 16-bit. Okay, but the memory address, okay, that we are dealing with is full 32 bits. Okay, that means the address range of the system, entire system, is full 32 bits. That means 0, 0, 0, 0, 0, 0, 0, 0, all the way. Okay, the full 32 bits come to FFFF and so on. Okay, so the full 32 bits is what the memory address sort of represents, is available to us, but the immediate field only has 16 bits of space. We only have 16 bits of space. So how do we do it? Okay, so that is where the idea of PC relative addressing comes in. Okay, the PC relative addressing comes in. So normally, okay, loops, when you translate them, okay, are not too big. Okay, and what it has been observed is the 16 bits is in most cases enough to cover the difference, okay, in the address range from where you execute to where you want to go to. Okay, so using that concept, it is easy to use the program counter as a form of baseline to decide where to jump to. That means instead of me specifying the full 32-bit, okay, so for example, this address is A0000000. Okay, so let's say this is the address that I want to jump to. I do not specify the full 32-bit address. I just specify 16 bits of where I want to jump to. And the other part of this final address is taken from my program counter. Well, the program counter is already a register that is part of the processor. Okay, it's always there. Okay, so we can make use of that information. So in terms of relative PC relative addressing, what we are saying is I can branch up to a certain range, either in the positive direction, that means I'm going to a higher address, or I can go backwards to an earlier address. Okay, so that is basically the idea behind this. All right, so the address is always what we call relative to the PC, relative to the program counter. Okay, and the way it is generated is it is the program counter plus the 16-bit immediate value. Okay, and the immediate value is a signed 2's complement number. All right, in terms of 16-bit, we know that the range is from 0 to 15, so you can branch up to the power of 15 plus minus locations. All right, now since we know that each location is actually an instruction, all right, so when you say it's 2 to the power of 15, it is actually 2 to the power of 15 words from the PC. All right, so in terms of bytes, okay, it is actually 2 to the power of 17 bytes. Okay, but again, what we are more interested in is this, that you can branch up to plus minus 2 to the power of 15 words from the PC. Okay, so we interpret it as words, okay, by automatically multiplying the information by 4. Okay, we will see this, okay, again and again, okay, in this as well as in the next chapter, and then you will sort of realize how this works. How come I can take this and I can multiply by 4 and then add and so on. Okay, you'll see that. Now, in terms of branch calculation, if the branch is not taken, your PC is always PC plus 4. All right, so what does this mean? All right, so your program counter, okay, so if your program counter is currently pointing to this address location, the moment I fetch this instruction into memory, your program counter will automatically point to the next. Okay, because your program counter is designed, okay, by design it will always point to the next instruction to execute. Okay, so if I already fetch the instruction at address 8, then the moment the instruction has been fetched, I will automatically point to 12, 8 plus 4. Okay, so that is how the hardware behaves. All right, so of course, if there is no branch being executed, then the natural address is always PC plus 4. Okay, PC plus 4 and so on. Okay, but if the instruction that I'm fetching is, for example, a branch, okay, then I may not execute PC plus 4, correct? I may go to some other location here. Okay, either after or before. So that next location that I go to, depending on if the branch is taken, would then be PC plus 4 plus an immediate value multiplied by 4. Okay, so this immediate value is basically the number of lines of instructions between the PC plus 4 and the line that I want to go to. All right, let's look at an example, then we can understand this better. In this question, in this example code here, the first line here is BEQ, okay, 90, and that means if the content in register 9 is the same as the content in register 0, I will branch to the end, which is here. Okay, now the next line here, okay, so let's look at it in terms of the BEQ sort of encoding. So RS and RT. So as before, this is your RS and this is your RT. So for BEQ, we take the first as your RS and second as your RT. Okay, and this is your opcode. Okay, for opcode, we look back at your instruction set summary here. So BEQ, you can see that the opcode here is 4. Okay, so we can come back here. So that part we know. Okay, BEQ opcode is 4, RS is 9, RT is 0. Okay, and the thing we do not know yet is what is the immediate. Okay, because for R type instruction that we saw, the immediate is actually a value which you can directly translate. All right, if I want to say add I T0 T1 with 5, that 5 is the immediate value which I can straight away represent in my instruction. But now what do you have? You have a label. N is a label pointing to some address location. Okay, so how do we do this? So what we need to do is we need to look at the relative address. Okay, so when my PC is pointing here and fetching this instruction, I already will increment to the next one. So this is PC plus 4. Okay, which is this instruction here. All right, so from PC plus 4, where is the N? The N is how many lines away? 1, 2, 3. Okay, so what you need to do is from the instruction that you fetch, first go to PC plus 4. Okay, and from PC plus 4, look at how many lines away is that label. So in this case, the label is 3 lines away. Okay. Okay, so the reason why we do not count the line is the hardware automatically increments PC to PC plus 4. Okay, automatically increments the PC to PC plus 4 the moment you fetch the instruction. So that is the default behavior of the hardware. So it is not software driven, that is hardware driven. So since the hardware already automatically increments by 4, okay, the offset has to be counted from that line onwards. Okay, from that line onwards. So in this case, we can see that it is 3 lines away. The label N is 3 lines away from the PC plus 4. So that is the N sort of actual address. All right, so that gives us the full encoding. All right, so all of this is actually done for us, okay, by the compiler. All right, when you write the code, okay, you do not think what is the immediate value I should put in this instruction. All right, you just worry about the label. Okay, so if I want to have a label, okay, I just use whatever name and I make sure that that name corresponds to where I want to jump to or branch to. Okay, so in our semi-language code, we do all this labeling, but when you compile, the compiler is the one that is actually calculating all this for us. All right, to make sure that when I encode this instruction, I have the correct offset that is loaded as the immediate value for this instruction. Okay, so that is how the final representation will look like. Okay, so how about replacing the last line here? So if I look at this instruction jump loop, okay, so jump we'll be covering in a while, but if let's say instead of jumping to loop, instead of taking that instruction, I can replace that instruction with this, okay, which is BEQ 00 loop. Okay, so of course, when I compare 0 register with 0, it will always be true. So this is actually another alternative of jump. Alright, so instead of specifying a fixed uh, instead of specifying as a jump instruction, I can specify it as a BEQ instruction, and since both the registers are the same, it will always be equal. So I will always take the branch and go to loop. So what will be the immediate value for this? Okay, so it again comes back to the same process. So when I fetch this instruction, PC is pointing here. But the moment I fetch this instruction, I go to here, PC plus 4. Okay, and from this line, how many lines of code to go back to loop? Okay, so from this point here, okay, so from this point here, I need to go back by how much? So from here, this is 1, 2, 3, and 4. Okay, so I'm going 4 lines back from PC plus 4. So since it's back, the answer is minus 4. Okay, so don't worry. Okay, you will slowly get the idea if you still have some issues. Okay, so if you specify it as -1, you will have infinite loop. Yeah. Okay, so if you were to write this as a -1, okay, then definitely when you come to the next line, you will come back to this line, and then there will be an infinite loop, and you're stuck there forever. All right. Okay, so let me just do this last part here. Okay, so let me just introduce you to the jump instruction first, okay, and then we can end it today. Now, the jump instruction is a bit different, correct? Because a jump instruction is what we call unconditional. Okay, because when we say jump, okay, we do not specify any condition. We just say jump to, for example, n, okay, whatever label. So there is no checking involved. So if there's no checking involved, that means there are no registers I need to read and compare or do anything. Okay, so coming back to our instructions, we can see that if you remember what I said just now, I need the first 6 bits for opcode. Alright, I need the first 6 bits for opcode, and since I need the first 6 bits, I can only have whatever is remaining after 6 bits. That means I have another 26 bits, okay, because total is 32 bits. Okay, so since I have 26 bits available, all right, of course that is good, but again comes back to the same issue is I need to specify a 32-bit memory, correct? Okay, we need to specify a 32-bit memory in our system. In our BEQ, we use the PC as the offset mechanism, correct? So we come back here. So we say that the PC will be the sort of baseline, and then from there we do the offset. Okay, so that helps us to overcome this thing. Okay, so but in jump instructions, I have more bits now. Okay, I have more bits. Okay, I have 26 bits. So how can I maximize this? All right, and to jump to as far as I can. Definitely, I cannot cover the full range of memory because we still have a limitation, right? We only have 26 bits. So what can we do? All right, so this is the format. Okay, so the opcode and the target address. All right, now what is the next step we can do? Since we can only specify 26 bits, what we can do is we can take the 26 bits and shift it to the left by 2 and add 2 zeros. Okay, why do we want to add 2 zeros? Because we know that all our instructions are word aligned. That means they're all 32-bit. So if they're all 32-bit, the last 2 bits will always be 0. Okay, so if you remember 0, 1, 2, 3, 4, 5, this was one of the first few slides. Okay, if you convert to binary, okay, you will see that whenever I have multiples of 4, the last 2 bits will always be 0. So this is 3, this is 4, okay, and so on. Okay, so you can see that whenever you have multiples of 4, the last 2 bits will always be 0. Okay, and since we are jumping to an instruction, the instruction will always have to be word aligned. All right, so that allows me to immediately take the 26 bits and make it 28 bits. Right? Because I know the last 2 bits will always be 0. Okay, and left is I take the 4 most significant bits of PC plus 4. Okay, and pad it with the 28 bits, and that will give me the 32 bits. Okay, so the full maximum range you have is 256 megabyte. Okay, so that is because of the 28 bits that you have. Okay, only the 28 bits you have are the ones that give you that range of memory, because the upper 4 bits are already taken from the PC plus 4. Okay, so you cannot still jump to the entire memory range, but you have more than enough to handle just about every possible case that you can come across. Okay, so it is definitely more than enough for the kind of code that we write. Okay, so basically what is happening is, if you have a 26-bit address that is specified in your instruction, okay, how do I take this 26 bits and generate a 32-bit address? I take the 26 bits, okay, I add another 2 bits, okay, and that will give me 28 bits, and then I take the upper 4 bits of the current PC plus 4, okay, and I combine everything together, and that gives me 32 bits. Okay, that gives me 32 bits, and that is the final address I can jump to. So definitely the range is much bigger compared to a branch instruction. Okay, so even though it may not cover the full address memory range, it covers most cases, okay, that you will need to apply this instruction for. Okay, so let's just do one example. So in this J format example, you can see that I want to jump to a particular address, which is this. Okay, so PC is here. Okay, and the target address that I want to jump to is here, address 8. Okay, so for this, how you specify? Okay, so the target address is specified in your jump instruction. Okay, now let's look at your PC. Your PC over here is 20, address 20. So they've given us that the address of the current program counter is address 20. 20, you translate it into binary, you get this. Okay, all zeros plus 101. And what do I do? I know that the address I want to jump to is this. Okay, address 8. Okay, so address 8 is given by this. Okay, how do I translate this address I want to jump to into the target address? I remove the lower 2 bits and I remove the upper 4 bits. All right, why do I need to do this? Because as far as I'm concerned, I need to make sure that when I reconstruct the final address, I go in the reverse order. Okay, what is the reverse order? The reverse order is I take this entire 26 bits, I add 2 zeros at the back, and I add the 4 bits in front, which is the current PC value. a PC+4 value. And this gives me the address I want to jump to, which is this. Okay, so you must think of what the processor will do to reconstruct the final address when I read this instruction. Okay, so the processor will do two things. It will add 2 zeros behind, and it will take the PC+4 and add it in front, and that will give me the final address. Okay, so that means when I want to put this in the instruction, I must do the opposite. I remove the last 2 bits, okay, and I remove the upper 4 bits, and that is what goes into the instruction. All right, so that is how you do the encoding. Okay, so I think we can stop here for today. All right, we have covered quite a bit. Okay, this chapter there's only a few more slides left, but I don't want to rush through. Okay, we can end it for today. So just a few things that yeah. So you can start to look at your QT stream and have a feel for how to go about starting off your assignment. Okay, if any questions, any doubts about that, you can ask me. Okay, other than that, yeah, I think we are going at a good pace. Okay, everything is going as going well. All right, so I wish all of you a happy new year. Have a good holiday and break with your family, and I will see you all again next week. Okay, so any questions you can ask me. If not, thank you very much. Good night.